Well, good morning or good afternoon, depending on whatever time it is, wherever you may be. And this is a continuation of the NASA Engineering and Safety Center, NESC Shock and Vibration Training Program. And my name is Tom Irvine, and I am an industry representative to the NASA Engineering and Safety Center. And I'm also a full-time employee of Dynamic Concepts Incorporated in Huntsville, Alabama. And I serve NESC via DCI. So we've been talking about natural frequencies and how they can be excited and characteristics of mass and stiffness and so on. And we've already covered the first half of these slides in the previous unit. So I'm just going to skip ahead to where we are next. And actually I'm going to just sort of review a little bit, a couple of slides. We've talked about how structures' natural frequency can be excited. And for the purpose of this course, there are four main ways we can do that. One is an applied force or pressure. So think about acoustic pressure or wind pressure or a turbulent flow over an airfoil, for example. Or you could think of a modal test where, for example, an impulse hammer is used to strike an object. Then the second way is base excitation. This could be a vehicle traveling down a washboard road. It could be a seismic excitation of a building, or a shaker table test where we have an avionics box mounted on a shaker table. There could also be self-excited instabilities or negative damping or airfoil or bridge flutter. And then there can be initial displacement or velocity, such as plucking a guitar string. And what we're going to be doing in the upcoming slides is we're going to go over examples of each of these type of excitations. So here's just a humorous, funny example. So here we have this man on his bike, and he's going over a bumpy road, and he's taking a spray paint can, and he's recording his vibration response to the base excitation from the road. Here's the 1989 Loma Prieta earthquake, and this is sort of the definitive photo from that earthquake. And if you think about the San Francisco Bay Area, parts of the bay, the edges of the shoreline, tend to be somewhat marshy and have a high water saturation and content. And after the 1906 San Francisco earthquake, some of the rubble from the destroyed buildings was pushed out to sort of reclaim some of these marshy areas and transform them into usable land. And also on other occasions as well, gravel and rock were taken to fill in some of these marshy areas. But the consequence of that is some of these areas are kind of, we would characterize them as being weak soil with a high moisture content. And if you think about the ground as being porous, during an earthquake there's different frictional effects occurring with these pores. And the moisture of the water is drawn up through the pores, and that can result in an unstable foundation. And that can even lead to extreme cases in something called soil liquefaction. So here we have the 1989 Loma Prieta earthquake, and the earthquake caused the Cypress Viaduct to collapse, resulting in 42 deaths. The viaduct was a raised freeway, which was part of the Nimitz Freeway in Oakland, which is Interstate 880. And this viaduct has two traffic decks. So you can see some segments of the upper deck collapsed onto the lower deck, and sadly that caused fatalities. So resonant vibration caused 50 of the 124 spans of the viaduct to collapse. The reinforced concrete frames of those spans were mounted on weak soil. As a result, the natural frequency of those spans coincided with the forcing frequency, or you might say the base excitation frequency, of the earthquake ground motion. The viaduct structure thus amplified the ground motion. The spans suffered increasing vertical motion, cracks formed in the support frames, and finally the upper roadway collapsed and slammed down onto the lower road. And the remaining spans, which were mounted on firm soil, withstood the earthquake. Now, this presentation is being sponsored by NASA, so why would we be interested in talking about earthquakes in a presentation that's oriented more towards NASA people? Although this is available to people in all other industries as well, including students. Well, one of the main launch sites for launch vehicles is Vandenberg, California, and that's located some miles north of Santa Barbara on the west coast of California. And this Vandenberg location is not very far from the San Andreas Fault. Well, if you think about a launch vehicle, it might be mounted on its pad for about a 2-week period before the launch actually takes place. And that period is needed so all sorts of different testing and fueling and different operations can take place. Well, there is an extremely, almost negligibly low probability that a major earthquake would happen during the 2 weeks that the vehicle is on the pad. However, if you think about the cost of the vehicle and its payload, and for certain missions that could be upwards of $1 billion. So we're putting $1 billion at risk, and it's actually common practice to do a seismic analysis on the launch vehicle as it's mounted on its launch pad for launches that are going out of Vandenberg. Now we're going to talk about the Pegasus launch vehicle. And again, we're talking about the different types of excitation sources. So the earthquake was base excitation. Now we're actually going to talk about initial displacement excitation. But first, a brief tour of what a Pegasus is. So this vehicle is intended to take a small satellite payload, which is not shown, but would be mounted about right here where I'm circling, into low Earth orbit. And this vehicle is kind of unique. It's actually carried by an L-1011 aircraft up to about an altitude of 40,000 feet. Then it's dropped for about a 5-second period, and then the first stage ignites, and it does a pitch-up maneuver, and it goes on its trajectory. Now, the L-1011 initially is mounted to Pegasus, or perhaps I should say vice versa, through 4 hook fittings. The hooks are in the L-1011, and they come down and they tie into these bathtub fittings. So during stage 1 burn, when Pegasus is still in the sensible atmosphere, this wing is used to provide aerodynamic lift. Now this first stage motor here is fixed, and by the way, these 3 motors are all solid fuel motors. First stage nozzle is fixed, but these fins on the aft skirt are movable. They're attached to actuators, and those actuators can provide the necessary steering and course correction for the Pegasus vehicle so it can stay on its proper trajectory. Then after first stage burn is over, it burns for about 70 seconds, there's a linear shape charge event to separate first stage from the inner stage. Then there's another linear shape charge event to separate inner stage from second stage. Now at this point in flight, the vehicle is out of the sensible atmosphere, and this stage 2 nozzle is gimbaled. It can rotate. There's a thrust vector control system, and that provides additional steering and mid-course correction for the vehicle as it undergoes stage 2 burn. And then the same thing, similar for stage 3, this is also a gimbal nozzle with thrust vector control. Now, most of the avionics are in this avionics ring here, or cylinder, but actually the avionics are boxes. There are boxes throughout various stations of the whole vehicle along its entire length. And there are 2, this is a clamshell fairing system, and during the stage 2 burn, these 2 payload fairing sections are separated and jettisoned away. Now there's also an inertial navigation system in this avionics section, and that has 3 translational accelerometers and 3 gyroscopes. And that data is taken, and there's various coordinate transformations performed and integrations. And based on that data, there's a software in the navigation system that can determine where this vehicle is as a point mass. In other words, where is the CG of the vehicle in space at any given point in time. And also that same software can determine what the attitude of the vehicle is. Now, based on the pre-planned trajectory and based on all that data, then the flight computer will issue commands to the various control systems to provide steering either via the fins or either of the nozzles, depending on which stage burn is occurring. So let's take a look at a Pegasus video here, and you can actually go to YouTube and look at a variety of videos, but let's see if I can call up this video here, if you'll be patient with me. So there the Pegasus in L1011. Now Pegasus is separated. It's undergoing a 5-second drop period. The first stage motor is igniting, and there's an angle of attack. It's doing a pitch-up maneuver. And as I mentioned earlier, the first stage burn will be about 70 seconds. And this video footage is being shot from a chase aircraft. So let's think about the shock and vibration environments that the payload will have to endure. So we might think, well, what's the worst case environment? Is it maybe first stage ignition or first stage motor burn? Is it the aerodynamic buffeting effects that occur as the vehicle undergoes transonic and maximum dynamic pressure conditions? Is it the various stage separation and payload separation and fairing separation events, which in some cases are linear shape charge or at least some type of a pyrotechnic device? Well, the truth is all of those are important, and all of those sources are important. They all need to be looked at. But as counterintuitive as it might seem, the worst case structural dynamics environment for the satellite payload is the drop transient. Well, why is that? Well, it turns out that as the Pegasus is attached to the L1011, it's bowing downward. Okay, here's the Pegasus here. It's actually slightly bowing downward due to the effects of gravity. And that places an initial strain energy or initial displacement on the Pegasus launch vehicle. And when Pegasus is suddenly released, then that initial strain or initial potential energy gets converted to kinetic energy, and that conversion takes place at the natural frequency of Pegasus. And due to the interplay of the stiffness and mass properties, there are a number of cycles of oscillations that occur. And if we look at some flight accelerometer data from Pegasus, well, first, before we do that, this is a finite element wire mesh model which shows the fundamental bending mode shape of Pegasus. So, and this is a highly exaggerated mode shape. So this would be the fundamental bending mode shape of a Pegasus launch vehicle. We're actually going to look at some data, and I've got a plot here, but instead of looking at this plot, let's just go to some MATLAB software where we can actually do this plot. Now, I've been talking a lot about my blog, and there's a couple ways you can get to my blog. One is if you go to the vibrationdata.com homepage and scroll down to the very bottom, there's a link to Vibration Data blog. And you can also get to it by simply typing in vibrationdata.wordpress.com. And I've got a section here on webinars. So here's webinar unit 1. And if you go to this blog entry, there's a number of links. You can get the PowerPoint slides, and there's links to the data, the different time histories we'll be looking at. So we're going to look at some drop transient data. This will be time in seconds and acceleration in G's. And there's also links to the MATLAB scripts, and all this may be freely downloaded. So one of the main programs we're going to be running is Vibration Data Signal Analysis Package. Then there's also sine and damp sine curve fitting. So if you click on this link, it will lead you to some MATLAB scripts that you can download. And we're actually going to run one of these on the Pegasus data. So let's go to MATLAB, and I'm going to get a little organized here. I'm going to close out whatever plots I may already have. And let's run a new program here. It's called SINEFDAM. And that stands for Sine Find Damping, but it's just abbreviated SINEFDAM. So let's click on this and see what this is going to do. So this program performs a damp sine curve fit for an input file, and the time history must be in a 2-column matrix format, time in seconds and amplitude, and that can be amplitude in G's or whatever amplitude you may have. We're going to pick an external ASCII file This is choice number 1, and it's going to be drop.txt, flight accelerometer data from a Pegasus launch vehicle. And the Y label is not shown, but it's acceleration in G's. So here, and it's versus time in seconds along the x-axis. So this is almost a textbook perfect damped sine function. So you can see there's some exponential decay of this envelope here. So our task at hand is to determine the natural frequency for the Pegasus bending mode, and also to find what the damping ratio is. So one very simple way is to count the number of peaks and divide by time. And if we go from 1 second to 2 seconds, you'd find that there'd be almost 10 positive peaks. So this signal is going to be about a 10 hertz damped sine signal. Just a couple of things more about this. When the vehicle is bowing downward, while it's still attached to the L1011, it's in a static deflection shape. Now, a static deflection shape is not the same thing as a dynamic mode shape. There could be some close similarities, but the two are actually different. So it actually takes Pegasus a couple of cycles to wiggle out of its static deflection shape and go into a pure dynamic bending mode shape. So that's what you see on the onset there. So we're going to do a curve fit, and the way we're going to do this is we're going to take a textbook damped sine function, and that has 4 variables: amplitude, frequency, damping, and then we could have some kind of a delay parameter as well. So what we're going to do is we're going to generate actually about 100,000 trial functions using brute force random number generation for those parameters. And each time we get a candidate waveform, we're going to subtract it from the raw data, and the idea is to minimize the residual error. So we want to come up with the best curve fit, and once we've done that, we've indirectly found what the natural frequency and damping are for this drop transient. So let's pick a time. We're going to skip over the first couple of peaks where things are kind of getting wiggled out. Let's start 0.4 seconds in time. And then we're going to go to, let's carry it out to about 4 seconds. Trials per frequency, we're actually going to run 100,000 trials per the one frequency we're going to look for. And that may seem like a lot, but it goes quick enough. We're going to be looking for one frequency. Now, this program, we can either put in the fact we already know it's about 10, or we can just use the lazy way, which is actually sometimes better, and say let the software automatically estimate what the frequency would be from the FFT and zero crossings. So let's do choice number 2, and then you're going to see real-time the curve fitting effect taking place. So each time the software finds a new best case, it updates the curve fit. So we've done 20,000 trial functions, 30,000. So the blue curve is our raw data. That's the measured input data. The green curve is our synthesized data. And we're doing pretty good so far, but maybe the software can do a little bit of fine-tuning. We get a pretty good curve fit there. It's I guess if we wanted to, we could go back and do 200,000 cycles to get it even a little better fit. But that's a good enough fit. And one thing we have to also take into account too is that the Pegasus drop transient is not a perfect textbook event, and there's always possibilities of some nonlinearities and even some higher modal behavior that's entering in. But for the most part, we got a very good curve fit. So this is telling us that the Pegasus drop transient has a natural frequency of 9.57 hertz, at least for this mission, if we truncate the last 2 digits. And the damping ratio, usually we like to present this as a percentage. So if we multiply by 100, we'd say there's about 1.1% damping. Now this is for a given Pegasus mission with a given payload. But each payload is different, and this natural frequency depends on the mass and stiffness properties of both the launch vehicle and the payload. So that's why it's necessary, one of the reasons it's necessary to do a coupled loads analysis prior to launch. A couple other things to think about is this is the natural frequency of the fundamental bending mode during drop transient. Well, what's going to happen during powered flight? Well, during powered flight, mass is going to be expelled. And when mass is expelled, then the total mass decreases, and the natural frequency is going to increase with time. So anytime we're looking at a launch vehicle, we want to know what the natural frequency is right as it's being launched, and also, actually for one that's ground launched, we'd want to know the natural frequency while it's on the launch pad, because we have to do wind and earthquake analyses. But then after it's launched, we have to figure out every 5 seconds or so what the natural frequency is going to be, because that's going to be changing in flight. It's going to be increasing in flight as mass is expelled. In other words, the fuel mass from the rocket propulsion system is converted into exhaust gas and expelled. So those are some of the things we need to look out for, and we actually need to convey that information to the guidance and control engineers, because as you remember, the Pegasus launch vehicle has an inertial navigation system with 3 translational accelerometers and 3 rotational gyro sensors. And those same sensors, well, they're intended to measure rigid body motion. And ideally, that's all they would do, is measure the rigid body motion, or you could say the CG motion. But in reality, those same sensors can potentially pick up the vibration as well. And we do not want a situation where the software, the guidance and control software, is mistaking structural vibration for rigid body motion. Otherwise, instability could develop. So the guidance and control engineers in some cases have to go in and put in a notch filter or take other measures in order to have stable gains and phase margins and all those things that they concern themselves with. So as vibration engineers or structural dynamics engineers, we have an opportunity to interface with the guidance and control engineers. Now, something else I want to talk about is we have a rule of thumb, and this rule of thumb is called the octave rule. So I'm going to type octave rule there. Now, the octave rule means that the higher frequency, I'll say FH for higher frequency, is greater than or equal to twice times the lower frequency. I'm going to type FL for lower frequency. And there's different ways this octave rule can be applied. But if we have 2 mechanical systems that are going to be mounted together, we want to minimize the effects of dynamic coupling, dynamic interactions, transmitted force. We want to minimize or mitigate those effects. So if we follow this octave rule of thumb, that means that the Pegasus payload should have a natural frequency of, let's round this off to 10 Hertz for simplicity. The payload should have a natural frequency of 20 Hertz or higher, or 5 Hertz or lower. And if it meets one of those 2 conditions, then it will satisfy the octave rule and minimize dynamic coupling between the payload and the launch vehicle. Well, as it turns out, only one of those 2 options is the right one, because we don't want a 5 Hertz payload. When I say a 5 Hertz payload, in other words, if we take the payload by itself and turn it into a cantilever beam, its cantilever bending motion should not be 5 Hertz or less, even though that would satisfy the octave rule. And the reason is, with that low of frequency, that could cause some interference with the control algorithm for the whole vehicle. It could also lead to excessive relative displacement of the payload within the Pegasus fairing, and we do not want the delicate solar panels of the satellite impacting into the inner walls of the Pegasus fairing. Otherwise, cracks or other failures might occur. So, as it turns out, the Pegasus payload should be 20 Hertz or greater than or equal to 20 Hertz for the payload's own cantilever mode. Now, I'd like you to fact check me on this. You can fact check me on this by going to the orbital.com website, and you can actually download a PDF document that's a payload user guide. And this is common. All the major launch vehicle providers publicly make this information available. And that user guide would say that this is the correct answer for the Pegasus payload. So that's the octave rule. Just keep that in the back of your mind. It's very useful for design purposes. And we'll be talking about that more as we go along in these course units. So let's see. We've just done a curve fit on the Pegasus launch vehicle, and for its fundamental bending mode during drop transient, and we know the frequency and the damping, and we can now convey that information to the guidance and control engineers, so that information can be used for future Pegasus missions. So let's close out of all those figures for now and go back to our slides here. So here's a different flight. Pegasus drop transient occurred. You can go back and look at that at your leisure. Okay, so another category is flutter, and this is kind of a fun one to look at. And we've actually have some wind tunnel test footage. Some of this was probably taken in maybe the late 1960s or early 1970s. And with flutter, there's all manner of different kinds of flutters, modes that you can research and study. But the classic one that's the most concern for airfoils is if the bending mode and the torsional or twisting mode coincide. And depending on the mass and stiffness distribution of the airfoil and other things like the turbulent boundary layers and Reynolds numbers and Struhal numbers and all that, there are certain cases where this flutter mode can get set up. So let's see if we can find the video links there for the flutter effects. So I'm fumbling around here, and let's see what we have. So this is a 747. So look at all that flutter going on, torsion and bending combined for those wing sections there. And presumably that effect has been, that potential has been mitigated by designs to the mass and stiffness properties to the airfoil, so that it does not occur on actual 747s in flight. But this is why wind tunnel testing is needed to identify these sorts of potential problems. So that's one example. Now here's a C5 tail. We're actually going to see two flutter modes. There we've got some twisting and torsion going on. Now it's going to transition to a different flutter mode. It's almost like a bird flapping its wing. So we got two different flutter modes on that video footage. So you might think to yourself, okay, well, that happens in wind tunnel models, but it would never actually happen in flight, would it? Or would it? So this is a twin Comanche aircraft. If we look at the tail section, this is in flight from a chase aircraft video footage. And you can see those flutter modes going on. And the immediate concern I would have is how will that interfere with the control algorithm. So imagine there was an autopilot, for example. Does the autopilot mistake that flutter motion for rigid body rotation? Or even if just the pilot is manually flying, does the pilot cause that instability to become even worse by the way he controls the vehicle? So that's the main problem. Of course, you might also say, well, even if the vehicle can still be controlled, it could cause some fatigue or other types of damage as well, and that's to be avoided as well. So that's some examples of some flutter for an aircraft wing. And I think the next will be the Tacoma Narrows Bridge. Let's see if we have Tacoma Narrows Bridge. So here's the Tacoma Narrows Bridge, and I encourage you to go to YouTube, and you can view all sorts of Tacoma Narrows Bridge newsreel type footage. So it had a torsional mode at 0.2 hertz. It was due to aerodynamic self-excitation, and the wind speed at the time of failure was 42 miles per hour, and the amplitude, and I assume this is a peak-to-peak displacement, was actually 28 feet, which is quite a bit. Now you can go yourself and look at Tacoma Narrows Bridge videos on YouTube. But I'll just show you one here.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million.
So there's the opening ceremony.
But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel.
This is the torsional vibration mode.
Third largest suspension bridge.
Two halves vibrating 180 degrees out of phase with one another. The cables vibrating.
Only at 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing.
There was actually a driver that fled from that car. There he is. He left his car, but he also left his dog. The dog was too scared to get out, so the dog was...
Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
I'm actually going to call up a paper I wrote on this and go over a few things with you here. So the Tacoma Narrows Bridge, it was open to traffic July 1st, 1940. It was located in Washington State near Puget Sound. At the time, it was the third largest suspension bridge with a length of, if we round up, 6,000 feet, including approaches. And the two supporting towers were 425 feet high, the towers being 2,800 feet apart. Well, it turned out prior to this time, most bridges were based on trusses, arches, and cantilevers, and they had to support the weight of heavy freight trains, including the cargo of the trains. But when automobiles, the automobile revolution came about, and automobiles weigh much less than a heavy freight train. So the civil engineers determined they could make these very elegant suspension bridge, not using as much materials, make them very elegant and economical to construct. So this became the favorite bridge design for automobile traffic. But unfortunately, they did not understand all the different types of forces and environments that would be acting upon these bridges. So we're going to talk about this failure a bit here. So initially there were 35 miles an hour winds, which caused the bridge's transverse bending modes to be excited with an amplitude of about 1.5 feet. And if you go through enough YouTube video footage, you can see some examples of that bending mode occurring. That lasted about 3 hours. Then the wind speed increased to about 42 miles per hour. In addition, a support cable at mid-span snapped, resulting in an unbalanced loading condition. So the bridge response thus changed to a 0.2 hertz torsional vibration mode with a displacement of peak-to-peak 28 feet. So here's the torsional vibration mode. Looking down the length of the bridge, you can kind of see the vehicle there. Then the vehicle eventually collapsed. So what was the mechanism of those various excitation mechanisms we previously discussed that caused the bridge to collapse? And was this an example of resonant vibration? And over the years, many explanations have been put forth. Some people said, well, it could be just random turbulence, but in order to get that sinusoidal motion set up, it did not seem that there would be enough energy at that frequency to be provided by random vibration. So choice number one was kind of quickly discarded. Periodic vortex shedding, it may have occurred either as a cause or an effect. Whether it was really the cause of the failure is probably something that's still being debated. And the other candidate was aerodynamic instability or negative damping. And choice number 3 is the one that I favor. But you can do your own due diligence and do your own research. Now here's a vortex street, just one sort of vortex street that can be set up. So if we have a blunt object here and we have the airflow going this way, now it depends on the geometry of this object. It depends on Reynolds numbers and Struhal numbers and coefficients of kinematic viscosity and obviously the speed as well. And depending on all those parameters, there are certain cases where these vortex shedding effects, these little eddies, will get set up. So did that occur with the Tacoma Narrows Bridge? If so, was it a cause or an effect? You decide. Yeah, that's your homework assignment. Build a scale model of the Tacoma Narrows Bridge and go to a wind tunnel. And actually, that's been done many times before. So here's a good explanation that explains what I and others believe happened. One of the characteristics of the Tacoma Narrows Bridge, if we look lengthwise down the bridge, and this is a cross section, is it had these box girders, and the box girders sort of block the wind in a certain way. And due to some initial, I'll call it angle of attack between the span and the wind, it could have happened because the cable at mid-span broke, as has been previously mentioned. So this wind got set up with an angle of attack relative to the bridge, and since there's wind here, there's high pressure here. Well, if the pressure here is higher than the pressure on the top side, then that's going to cause force and moment type of effects to occur. So the resulting moment is going to make the bridge want to twist. So as the bridge span twists, then that span becomes more and more towards perpendicular with the wind. And as that happens, the pressure increases and the moment is reinforced. So the motion of the bridge is reinforcing the very pressure that's being placed upon it. So the bridge starts rotating counterclockwise. Again, as it does so, the pressure becomes even greater because the wind is moving towards a perpendicular orientation with the span. But eventually this rotational stiffness affects the potential energy, the induced strain energy builds up to the point where the bridge no longer wants to rotate anymore, even though this wind pressure is increasing. So when that happens, it abruptly starts snapping back. Well, it's going to actually overshoot its rest position, and the reason it's going to do that is because it has mass and inertia properties. So now it's overshooting its rest position, it's rotating counterclockwise, and now this wind pressure is greater on this top side. It's reinforcing the motion, and as the bridge continues to turn, that pressure and that moment, resulting moment, become even stronger. Well, eventually, again, the rotational stiffness effects cause the bridge to then turn back and begin rotating clockwise. Well, after a number of failures, fatigue cracks start being developed and propagating, and the bridge fails. And so I would call this a bridge flutter, self-excited or negative damping type of effect that occurred. Now, another thing to think about is we're assuming that this wind is steady wind. And an oversimplified way to think about this is that there was no frequency content in the wind that matched the 0.2 hertz torsional oscillation frequency. And if you want to be more circumspect and precise, really we need to start talking about something called a Struhal number. And we could say that the Struhal frequency did not coincide with the bridge's torsional frequency mode, or the frequency of the torsional mode. So that's a roundabout way of saying that this was not a resonant type of effect. Now, in some sense, it was a resonant-like response, but it was not a true resonance. Rather, it was aerodynamic instability or flutter. So let's kind of move on a little bit here. And in 1950, the replacement bridge opened up. And what were the design changes? Well, instead of having those closed box girder plates, an open framework, open beam framework was used so that the air could pass through instead of being blocked as it was with the first bridge. And also, as you can see, that underlying beam framework adds a tremendous amount of both bending and torsional stiffness. And if you were to go to the Tacoma Narrows bridge today, you'd actually see there are two side-by-side bridges so that traffic can go on, the northward traffic can go on one bridge and the southward traffic can go on the other bridge just to improve traffic flow. So maybe some of you have had an opportunity to do that or will in the future. And by the way, this paper is called Tacoma.pdf, and it's posted at the webinar page, so you can go back and look at this at your leisure. And in the kind of the appendix area here, I just have some very introductory information on what a Struhal frequency is and a Struhal number. And basically, if we take into account the geometry of the bridge, its dimensions, see those box girders there were 8 feet high. That was part of the problem. I would find out that the Struhal frequency for that particular 42-mile-an-hour wind condition had a content of 0.84 hertz. Well, that's more than 2 octaves higher than the torsional oscillation. So I would say that's not resonance. And I'm being a purist in that sense, but if you go to some authoritative physics textbooks, this bridge will be cited as the all-time classic example of resonant vibration. Okay, enough about Tacoma Narrows Bridge. Let's go back to our slides. Okay, this is something interesting to think about helicopters. So we've done base excitation example. That was the Loma Prieta earthquake. We did initial displacement. That was the Pegasus drop transient. And we've just done Tacoma Narrows Bridge, which is aerodynamic instability. Now we're going to talk about an applied force. So anytime we have rotating shafts or imbalance or shaft misalignments or things going on with bearings or whatever, those type of machinery type vibrations are actually applied forces. So if we model this helicopter, this is while it's still on the ground, we could model this helicopter as a spring mass system with its mass, stiffness, and damping. And the rotational that's going on with the main rotor hub could be modeled as the applied force to the spring mass system. And then we could carry out the calculations, which we'll do in future units to see what the response would be. But now think about this vehicle. This helicopter is preparing for its takeoff. So now the main rotor hub is spinning up, and it's undergoing an angular acceleration to spin up to its full speed takeoff angular velocity. Well, what's going to happen inevitably? At some point, that rotational frequency is going to produce an oscillating force which coincides with the natural frequency of this whole helicopter as mounted, as modeled as a spring mass system. When that occurs, there's the danger of resonant response. So in order to mitigate the effects of resonant response, there's 2 or 3 things we want to see happen. First of all, that angular acceleration rate should be high enough that we do not dwell at the natural frequency of the helicopter. If we dwell at the natural frequency of the helicopter, then we get ground resonance effect, and that can be catastrophic, actually. The second thing is when a structure is undergoing resonant vibration, its response is very much controlled by damping. So we want this system to have enough damping built in to minimize the response of this mass, or in other words, the helicopter body, as this potential resonance is encountered. And the third thing we want is we want the pilot to be trained so that if for whatever reason this resonance does start to occur, that he pulls back on the yoke quickly in order to get up off the ground. Because once the helicopter is off the ground resonant possibility just goes away. So one of those is pilot training, but you know, an ounce of prevention is worth a pound of cure. Would rather designed the system so it had enough damping and so that the angular acceleration was quick enough so we mitigate potential resonance effects. So you might think, okay, well, that's nice. Well, but it actually can be a very serious thing. Now here's a TH-55 helicopter. Same model numbers, different serial numbers. The top is how the helicopter should look. Well, in the bottom, the helicopter just had a catastrophic failure, and it was due to a ground resonance effect. So this can be very serious when it occurs. And we've got some fun videos to look at. You can actually go to YouTube and look up some videos yourself, but I'm going to show you an example here. And I think the moral of the story is it's a bad idea to take a helicopter and chain it to the ground. This was a test. So this particular Chinook helicopter was having some engine vibration problems. So the test engineers got this idea they would just chain it to the ground and run up the engines so they could study the vibration problem. This was not test to failure. That was not the purpose of this test. But look what happens because of the ground resonance. That whole back blade assembly, and it's a tower or turret, whatever that's called, it just has a catastrophic failure. So if you're a U.S. citizen, that's your taxpayer dollars at work. Okay, that's just the same video there. So ground resonance is a it's a potential serious type of effect, and it's also, for the purpose of this course, an example of applied force excitation for a system. Okay, what else? Let's talk a little bit about guidance and control systems. I think we talked about this already. If we have a rocket vehicle with a closed-loop guidance system, its own sensors, they're intended to measure rigid body acceleration, but they can also pick up the elastic body structural oscillations, and that can interfere with the control algorithm. So we need to have the proper software with the proper gains and phase margins and stability. And the guidance and control engineers, they go off in their own world and they do their Nyquist plots and their Bode plots and look at poles and zeros. And but this needs to be accounted for. And a more kind of common household example of this is think about a hard drive. So a hard drive on a laptop or a desktop PC, and that's a series of concentric disks with some read-write heads. Now those read-write heads have to go to a certain place and time in order to either send or receive data from the metallic disks. Well, what happens if there's some vibration going on? Well, what can happen is those read-write heads could go to a certain place and time to do their data transfer, and oops, that location is not. It's the wrong place. So what happens to happen is the disk has to spin around one more cycle in order that the read-write heads have another chance to transfer the data either back or forth. So that's called I believe it's called a latency defect. And so you have to remember the hard drive on a computer, it also has its own closed-loop guidance system or control system. And vibrations can interfere with that. It can interfere with the performance, and in a worst case, it could cause a heart failure. But even if there's not a heart failure being provoked, there can still be a loss of performance with that hard drive. So sometimes people think, well, I've got a hard drive. I need to mount it on a vehicle that's undergoing vibration, and I'm going to mount it via isolators. Well, that might not be such a good idea because that low isolation frequency you're going to set up could interfere with the control algorithm. So if you need to, because the guidance and control engineers that well, I'm calling them GNC engineers as if they were aerospace engineers, but you get the point. Those control engineers most likely assumed that hard drive was going to be hard mounted. So if you need to isolate a computer hard drive, you need to contact the vendor to discuss the potential for either latencies or errors or hard failure if it's isolated. So I think what we're going to do now is bring this unit to a close, and we've got another unit coming up that will finish off natural frequencies. And again, what I encourage you to do is please make ample use of the vibration data blog. And there's all sorts of things here that the curve fitting programs we've run are posted there. There's plenty of other things as well, different MATLAB utilities and different topics of interest. And of course, if you go to Webinar Unit 1, you can pick up the PowerPoint slides as well as the tuning fork data we did previously, drop transient data, the Slinky video, which also has an audio track, different tuning fork mode shapes, and so on. So everyone, have a good day, and we'll see you the next unit around.